What we'd like to talk about now is what are known as the solubility of sparingly soluble salts. Now, sparingly soluble simply means that a particular substance, a particular compound that we call a salt is not particularly soluble. Let's show you what I mean. If what I have is known as a soluble salt, something like sodium chloride. Now, you know sodium chloride is a soluble strong electrolyte. So let's say I take a chunk of sodium chloride, that's sodium chloride right here, and I put it in water. It immediately begins to dissociate almost instantaneously into sodium cations and chloride anions. And that's what's floating around in solution almost exclusively. There's virtually no, as long as I have an unsaturated solution, virtually no intact sodium chloride in the solution. On the other hand, if I were to take what we know as a sparingly soluble salt, which would be calcium fluoride, and I were to put that in water, well, here's what happens. You drop that in water, first thing that happens is you get a little bit of a splash, and then that calcium fluoride goes to the bottom and it kind of sits on the bottom as a solid. And we say, well, the calcium fluoride, it's just sitting down here as a solid crystal in a solid form, completely undissolved. Well, that's not precisely true. Actually, there is a small equilibrium. That is, some of the calcium ions and the fluoride ions will dissociate from the solid. So you'll have a little bit, tiny bit of calcium 2+ floating around, and you'll have some fluoride ions. That is, there's 2 fluoride ions for every 1 calcium ion as this calcium fluoride dissociates. And that's what we call a sparingly soluble salt. Well, as it happens, since this is a sparingly soluble salt, we get an equilibrium. It's a two-way reaction. We get the dissociation, calcium fluoride to calcium fluoride ions, and then again, some of the calcium ions and some of the fluoride ions go back together to form the solid calcium fluoride that's sitting on the bottom of the beaker of water. So this is calcium phosphate. And as calcium phosphate, a sparingly soluble salt, dissociates, every time 1 mole of calcium phosphate dissociates, I get 3 moles of calcium 2+ ions in aqueous solution, and I get 2 moles of phosphate 3- ion in aqueous solution. And that gives us the equilibrium reaction for the dissociation of this sparingly soluble salt, calcium phosphate. Here we have ammonium sulfate. Every time 1 mole of ammonium sulfate dissociates, we'll get 2 moles of NH4+, and that's in aqueous solution, plus 1 mole of sulfate 2- ion in aqueous solution. So that is just a representation of the equilibrium reaction, very similar to all the equilibrium reactions that you have been writing so far. Well, since this is an equilibrium reaction, then there must be an equilibrium constant expression. Ksp stands for solubility product. And that is simply the result of the fact that we have not particularly soluble compound that dissociates to a product. That is, the product represents the solubility, what we'll come to know as the molar solubility in just a bit. So Ksp is equal to the solubility product. That's what Ksp means. And don't get hung up on that. It's just another equilibrium constant expression, or an equilibrium constant in this case. And since we've got calcium with a coefficient of 3, that would be calcium ion, Ca2+, in brackets, raised to the 3rd power. And then over here we have phosphate, PO4, 3-, and since its coefficient is 2, we raise that to the 2nd power. And there is our equilibrium constant expression that is associated with the dissociation of calcium phosphate. For ammonium sulfate, it would be similar to that. We have Ksp is equal to the ammonium ion NH4+, and since the coefficient is 2, we go ahead and we square that term times the concentration and molarity of sulfate 2 minus ion. There we go, 2 minus. So here is the equilibrium constant expression for the dissociation, which is an equilibrium process. Anytime you have those equilibrium arrows going in both directions, what we're saying is at equilibrium that calcium phosphate is dissociating at the same rate that calcium phosphate is forming. So, and here are the equilibrium constant expressions that we associate with those. So you knew this was coming. Since we have an equilibrium reaction, we're going to be doing calculations of the molar solubility, or the number of moles of the product of the dissociation in our sparingly soluble salt. So here we have our first problem. Our first problem says that calcium fluoride has a Ksp. Now just remember, Ksp is just another equilibrium constant. And what we're being asked to do in this problem is calculate the concentration of fluoride ion in a saturated solution. So what we want to do first is calculate the number of moles of calcium fluoride that may be dissolved in 1 liter of solution, and then we'll work from there. So let's just start out with the chemical reaction. And you know this is the hard part, is figuring out what is the chemistry. So here we have our sparingly soluble salt, calcium fluoride. It's going to dissociate. And whenever 1 mole of calcium fluoride dissociates, it dissociates to 1 mole of calcium 2+ ion, which is going to be an aqueous solution. But notice that we've got 2 fluoride ions that are going to be in that solution as well, each time 1 mole of calcium fluoride dissociates. So we have this equilibrium expression. Now, like any other equilibrium reaction, we can use an ice table associated with that, ICE. Let's look at it this way first. All right, so initially, I have some mass of calcium fluoride. I don't know what its concentration is. That's related to its density. And since it's in a solid form, I don't care because it won't affect the equilibrium constant expression. I start out with no calcium ion, no fluoride ion, and my change is going to be minus X, but since this is a solid, it's not going to figure in my equilibrium constant expression, but I'll put it there just for demonstration purposes. So every time 1 mole of calcium fluoride dissociates, I get 1 mole of calcium ions, but I get 2 moles of fluoride ions. And then I go ahead and I just add up my equilibrium lines, and I have 2X of fluoride ions, and I have X of calcium ions in solution. So I'm going to go ahead and write my Ksp expression just as I would any equilibrium constant expression. So that's going to be calcium 2+ times the fluoride ion, and we're going to go ahead and square that. So it's just the fluoride ion concentration squared. Now I get a lot of folks that want to understand, well, why don't you put a 2 in there? We don't put the 2 in there because this is the fluoride ion concentration. I'll show you where the 2 comes in, other than simply raising the fluoride ion to this second power because of the coefficient of the 2. Here we go. Let's go ahead and just substitute in our ice table values. Well, for calcium ion, it's just X. But for fluoride ion, it's 2X. And now let's do to the X values exactly what we did in our equilibrium constant expression. So for X, it's just X to the first power times 2X to the second power. Well, 2X to the second power is 4X squared, and then we're going to multiply it by 1 more X, and when we do that, we get 4 2x cubed. So we put the 2x in place of the fluoride ion because that's what's in solution when we get to equilibrium, 2x. Because there's 2 fluorides for every 1 mole of calcium fluoride. So now I'm going to substitute the Ksp, which is 3.9 times 10 to the minus 11, which is equal to 4x cubed. And I'm going to go ahead and solve for x. And if I solve for x, I have to divide both sides by 4. That gives me x cubed, and x cubed is equal to 9.75. 9.75 times 10 to the minus 12. And how do I get rid of the cube term? Well, I take the cube root. Now, if you don't know how to take the cube root on your calculator, I'm going to give you a really easy way to do it. In your calculator, go ahead and put the 9.75 times 10 to the minus 12 in parentheses, and then use the little caret indicator, the little pointy thing like this. It raises it to a power, and raise it to, and you need to be very careful about this, open up a set of parentheses, and we're going to raise it to the 1/3 power. So this is the same as taking the cube root of 9.75 times 10 to the minus 12. It's just a different way, raising it to the 1/3 power. If we wanted to take the 4th root, it would be to the 1/4 power. Or if it's square root, you can actually take it to the 1/2 power. Just raise it to whatever power for every whatever root that you want to determine. So here we go. So x, which, by the way, we call the molar solubility, x, in this case, is going to equal 2.14 times 10 to the minus 4 molar. I'm going to go ahead and write that over here. X is equal to 2.14 times 10 to the minus 4 molar. All right, and this is what we call the molar solubility. I'm going to repeat it a few times so you actually get that. And whenever you're working these problems, what I want you to remember is that X is always going to be the molar solubility. All right, so now what we have to look at, since what we're looking for is the concentration of fluoride ions in a saturated solution, we see right here that the concentration of fluoride ions is actually equal to 2x, not simply x. So the fluoride ion concentration that's in solution at equilibrium is equal to 2x, which is just 2 times 0.14 times 10 to the minus 4 molar. And when we do that, we get the fluoride ion concentration. Looks like 4.28 times 10 to the minus 4. So I think we'll stop there and continue on in another video.